Welcome to the pre-recording of the second lecture of MCS 260, a course introduction to computer science. So this is our second lecture, but in a way we restart. So this lecture is very much a reboot of the last lecture, which I hope was not too confusing. Last lecture gave more an overview. What you should remember, if there's one word, is algorithm. So in this lecture we will talk about numbers. The arithmetic, which we often take for granted, is a rich source for algorithms. And computer science is the systematic study of algorithms to describe and transform information, as we have covered last time. Today we take a very hands-on approach, so there is a Jupyter notebook waiting. So I have prepared the Jupyter notebook, but unlike last lecture where I just scrolled through completely formatted and completely worked Jupyter notebook, I will now take the time to demonstrate how to make a notebook. How to follow this course. Notebooks refer to taking notes. I am a conventional guy, and the way I would go through these lectures, I would take pen and paper and take notes, but then also transcribe this into a Jupyter notebook. Or you could, as I would imagine in a more modern fashion, have a Jupyter notebook open and take notes. So the most important resource for this course will be the notebooks that you make throughout this course. All right, let's then dive into the material. I will first explain the environments that make programs work and run. And then in the second part, the computer literacy, we need to be aware of the binary and hexadecimal notations of numbers. Okay, we distinguish hardware and software. So hardware is everything that is physical, so the physical computer. Computer science is not the study of computers. In some sense, the name is still awkward, and we can do computer science without computers even. But still, why not use a computer? So we think binary, so this is a very shallow slide in a way. There will be a lot of terminology, no formal definitions much, but more hardware compared to software. Hardware is everything that are the physical components of a computer. Software are the programs. And then we distinguish the hardware into the actual computer and what are the peripherals. Now, of course, what is the actual computer? I'm running this pre-recording on a laptop where actually everything is one piece, except, for example, the power cord, but the screen is actually a peripheral, even if it's attached to the laptop. The computer itself consists of the processor, the memory, and the bus. Software is also very crudely organized in two pieces, in two parts. We have the basic software that is called the operating system, and then there is the application software. We will go later into operating systems more deeply, but for now, the distinction between operating system and other software is every other software needs an operating system to run. So when you have a computer, you turn on the power. If there is no operating system, then there is very little that you can do with the computer. So if you like, the operating system is the essential software. In the past, it was very important that one could distinguish between Unix and Windows or Unix-like systems, but there is a convergence. So there is the Windows subsystem for Linux that you can install on the Windows computer. Linux computers, they have very nice graphical user interfaces, and from a user perspective, the distinction starts to fade a little bit. Of course, it is still very critical to know on which operating system you work. Okay, um, more terminology. How do we, when we talk about hardware, I will try to indicate what you need to know as a user and programmer of a computer. So all programs, all instructions are executed by the processor or the central processing unit. The processor also coordinates the transfer of the data from memory and from storage into memory to the registers that are close to the processor. So in some sense, I shouldn't have mentioned the word register, and I cannot take it back now. But if we think about where the data resides, we distinguish between volatile and persistent storage. Memory, it's also an awkward word. Humans have memory, and often the distinction between memory and storage is that with storage, it's just storing something. Memory refers to an organization and an intelligence to do something with the data. But here we use memory and storage to make the distinction between the volatile and also much faster memory, the random access memory, as it is called as well, that stores the data and the programs, and then the storage that stores things permanently. You could think physically, storage resides on your disk or on also an external device. I'm using actually a flash drive to transfer data between my laptops and my Linux workstations. Not using the internet, which has the benefit of backup. So I have my data almost everywhere. So processor, memory, storage are the three main components of a computer. Of course, without peripherals, without keyboard, without screen, you cannot communicate with a computer. Well, you can communicate. Also, there are other input devices and other output devices than just a keyboard and a screen. But peripherals, they are also essential. And then there is what is called the system bus to connect all the components. The CPU, the random access memory, the storage, and the peripherals. So this gives us words to talk about hardware. As a programmer, it is critical that you know the distinction between memory and storage. You can do very nice computations, but once the computer is turned off, you don't want that they all get lost. So our programs will actually also reside foremost in storage. Okay, programming environments. That's the second part of this first part of the lecture. More words. What is a programming environment? Well, it consists of an editor. An editor is what you use to type in your instructions. Then there is the compiler and the interpreter, or I should say compiler or interpreter. So when we type source code, we write it at a very high level. It needs to be translated into executable code. A piece of executable code is called an object. So we have source and object. The compiler will translate it. It will be linked into one single executable program that will be executed. The interpreter does everything at once. It takes the source code, translates it, and executes it very conveniently. However, there is a drawback. If you are running the same instructions all the time over, and we have seen last time, and we will see that again, that every program most likely has a loop, then actually all the instructions that are executed in the loop are translated and translated again. Computers have become extremely good, extremely fast, and we don't really care about this anymore, but compiled code is typically a lot faster. Now, what is important for Python is that Python is an interpreted language. So Python is the programming tool that we will be using. Python is quick in a way for us humans, in the sense that we don't have to compile it, we don't have to link it and then run it. No, it does everything all at once. Very convenient. Then there is the debugger. In an ideal world, we would always write software free of errors. But as the saying goes, a program free of errors is a trivial program. And that is a scary statement, but it applies to very, very large software systems, which always have errors in there. Okay, the red letters here is what you should remember from the slide. So Python is interpreted. More about this on the next slide. Then there is the integration. So we will be using JupyterLab, which may at first be quite complicated and daunting, but JupyterLab integrates all of them. Python is a language that comes with batteries included. So if you install Python, you most likely will also install the integrated development environment. That's a serious word. In Python, Python is named after Monty Python. In Python, the integrated development environment is called idle. Somehow a pun as well. We will use JupyterLab, and in the second part of this lecture, I will demonstrate how we will use JupyterLab to develop our programs. Okay, the operating system is, if you like, a shell around the hardware. The Python interpreter is actually another shell between the operating system and the programmer. So that's why we call it high-level programming languages. A low-level programming language, although I do not use that word. Assembler has a lot of advantages. Assembler, which we will not cover here, is a language which allows to write programs directly into the basic instructions. Everything in a computer is binary. What an assembler actually does, it provides symbols for the basic instructions. Learning how to program in assembler is a very excellent way to learn how computers really work, and still at the high level. We will not do this in this course. So, but you have to know that the Python virtual machine translates the source into what is called bytecode. And then the bytecode is executed by what is called the Python virtual machine. So the Python virtual machine will negotiate with the operating system. So many layers in between you and the processor in the central part of the computer. Again, why doing this? Well, at the end of this course, we will be capable of prototyping a basic video game. So the advantage of this high level abstraction is that we can work in some sense much more efficiently in terms of programs, the usefulness of programs. Okay, so some personal concepts. So computer science was done by people. If you have to know one person for modern computing, then it is Alan Turing, who is known for the Turing machine, which is an abstraction of a computer introduced in 1936. You should also know him from the Turing test. Can we distinguish a computer from an intelligent human being? So still very, very actual as today, although already foreseen in 1950. In the last lecture, I mentioned ACM, the Association for Computing Machinery. There is the Nobel Prize of Computing. So there is no Nobel Prize for Computing, but there is the Turing Award. A more personal introduction to computer science would be to go to the website of the ACM, acm.org, and look at all the ACM Turing Award winners and see what the contributions are of those people to the field of computing. That could be another way to introduce the subject. Okay, we are not following that road, but I think this is a course on computer science, and every computer scientist needs to know who Alan Turing was, and the Turing test, the Turing machine, and the Turing Award. All right, number systems. So in some sense, we take numbers and arithmetic for granted, but they are a very fertile ground to define algorithms. So an algorithm is an ordered set of unambiguous executable sets that define a process that terminates. So this is the definition that we gave last time. So if we think about numbers, so think about the number 284 as written here, then this number assumes that we use the base 10. For us, it's obvious because we have 10 fingers. That's why we are using base 10. But it's not at all that obvious that base 10 is the best base to compute in. A computer will compute with the binary number system. So that's why if you write a number, you shouldn't actually write it as 2 to the power 10 to the power 2, or 8 times 10 to the power 8 and 4 times 10 to the power 0. That would be very, very cumbersome. However, you could write underscore 284 underscore 10 to make the distinction that you are thinking decimal. So the larger the base, the shorter the numbers, but the more symbols that you need for the digits. So a digit is saying actually a finger, so that's a digit. But we also talk about hexadecimal digits. And typically we don't really have 16 fingers, although you could imagine for binary we have 2 hands. If you only want to use one hand, then you can use base 5, and here you can see how you convert from any number system into the decimal notation. And that conversion consists of writing down the large or the long way to write numbers, explicitly using the base, and the power is the position. So we read the numbers from left to right. So when we think about the powers, we read the numbers from right to left. So, and we start counting from 0. So the rightmost number has power 0. The first number, the power is the number of digits plus 1. I'm sorry, minus 1. So you see, it's confusing to start from 0. Okay, so introducing algorithms by example is something that we do in calculus, prerequisite for this course. In this course, that's actually not good enough. So one exercise is already to define the algorithm to convert from any base, you can start with base 5, into the decimal notation. The middle bullet on the slide illustrates the general formula for evaluating a and I already said the word almost, evaluating a number in any base into the decimal notation. You actually evaluate a polynomial, but where you evaluate is the base of the number system you're going from, and you do your arithmetic in the base 10. So I'm actually also solving an exercise, but I'm going now more into the abstract. So if you want to convert from any base to any other base, you evaluate a polynomial in the source base, and you evaluate with the arithmetic of the destination base. So if the calculation that is done at the bottom of the slide is calculating in base 10. But if you want to convert to base 8, to the octal, then you would evaluate the expression, the long expression in base 5, you would evaluate it into the octal system using the octal arithmetic, using the octal digits. 8 bits is a byte, by the way, so that's why the octal is also a system that we consider. Okay, binary numbers. We have been doing the binary classification very good to distinguish one from the other. A lot of advantages thinking binary, but you have very long numbers. You can group them in groups of 4, and that gives then the hexadecimal number system. So you run out of ordinary digits, so we then resort to the letters of the alphabet. So 10 is written down as A, 11 is B, C is 12, D is 13, E is 14, and F is 15. So these are the first 16 natural numbers. So converting from hexadecimal into binary is looking at the table and translating every hexadecimal digit into a sequence of 4 bits. Converting the other way is a little bit more complicated. You start from your bit sequence start at the right, and you group all the bits. You replace every sequence of 4 bits by the corresponding hexadecimal digits. If I have to, I hope that as you as the reader who looks at this, that this is clear. But these are ideas for algorithms. So if you start thinking as a computer scientist, you will see algorithms everywhere. So it's an excellent exercise to translate the 2 statements into actual algorithms and pseudocode. First, start with the specification. What is the input? What is the output? And then very clearly and in an orderly fashion, define the steps of the algorithm that translates the input into the output. Okay, I'm 25 minutes in, halfway. Let me now go to an algorithm. So this is an algorithm that we will code up. If this lecture goes too slow for you, then you can look ahead. We will introduce the Python code to execute this algorithm. I'm introducing an algorithm here numerically. We convert any decimal number into a binary format by dividing by 2. Dividing by 2 and taking the remainder by 2. So the n mod 2 is the remainder that is the result from the division by 2. You see we have an 1 for the odd numbers, 0 for the even numbers. We keep on doing this, so this will terminate. So reasoning about algorithms is that the number n will actually turn into a bit. It will turn into a 1 or a 0. If it is a 0, then we stop. So as soon as the quotient becomes 0, we stop. So I'm already thinking ahead into an algorithm, and we will formulate this algorithm. So you see, you can look at an algorithm in time. You can read this table from the top to the bottom, but you can also read it from the bottom to the top. So the rightmost column describes the rewrites of the numbers. And actually, it suffices that you remember the bit sequence. So the binary representation of the numbers is the sequence of remainders. It comes out in the opposite order. We actually compute the least significant bit first, and the most significant bit, the first bit, we compute last. So this is an algorithm, but it's not an algorithm. So if you look at, so as a human again, so you can now execute this algorithm by paper and pencil. This is not this type, of course, although it would be good actually to translate this into a Jupyter notebook. I haven't done this, but Markdown allows you to typeset this table. If you are interested in Markdown, a good exercise is to look up the format to typeset this table in a Jupyter notebook. And do this for another number than 1, 2, 3. Okay. Flowcharts. Here is the representation of the algorithm. This is now the algorithm of the previous slide with a picture. So there is the decision. So if you use the diagram, which I did not do in this, which I will not do in this lecture either, but I did it in the last lecture, you could practice to use the diagram of the Jupyter notebook to typeset this. You can start with the diamond, so that's the decision. As long as your number is not 0, so that's actually the quotient, we replace the number by its quotient. That is what is being done. We compute the remainder and the quotient, as long as, and we print the bits. So we print each remainder. And we continue this algorithm as long as the quotient, as long as we have a number that is different from 0. Okay, I'm more than halfway in this lecture. Let me point out to the exercises. Last lecture I described the installation process. We sketched the difference between source and executable, also called a binary. Explain the difference between installing software from source and installing executable versions of the software. How can you tell? You can tell when you go to a website and it asks you to decide on your operating system. That's already a telltale sign. What's the main difference as a user when you install the source? In some sense, this is advantageous that you can own the instructions, own in the sense that you have the source, but then you have to compile it. You have to build the software. So sometimes you may not want to do this. Exercise 2 you will be able to do at the end of the second part. Exercises 3, 4, and 5 are exercises that you should be able to do right now. So in particular, the last exercise is actually the most complicated one. I sketched it by saying if you convert a number from any base into a number of any other base, you do the arithmetic in the number system of the destination, and after converting the source number into the base. Now, describing the algorithm in great detail, again, I won't repeat the definition, in executable steps is not trivial. So running this by hand, going from 5 to octal, is something that you should be able to do right now. But describing the algorithm very precisely is non-trivial. So I do not want to trivialize the difficulty here in this course. Okay, I originally had budgeted only 20 minutes for this part, but I'm spending perhaps a little bit too much time on this. Let me now go into the environment. So here you see there are two tabs. So actually I'm only showing you part of my JupyterLab environment. So here you see my entire environment. So if you do not want to see my face, then perhaps that's a more favorable view. So this is my complete environment. So if you would be worried that something is too much in your view, so here is the complete environment. But actually the relevant part of what I want to show, I will move that again. Okay. I was talking about an integrated environment. So if you launch JupyterLab from the first time, what you actually see is the environment here. And you can see it's a little bit confusing perhaps at first. And in last lecture, I should have explained this, but I explained the complete. So in some sense, this is a reboot. You see the text file. This gives you the editor. You see that in this environment, it's rather Spartan. I said Jupyter stands for Julia, Python, and R, but I'm running this on a new laptop and I have not installed Julia on it, and not R either. So it might be that you see many more kernels there. You also see the terminal environment. I will be using the terminal. I will also be using the notebook environment. You see here the flowchart. You could also go to a more basic markdown environment. Okay, let's go to the notebook environment. I have already prepared this, so here you see the first steps notebook. This is what I will post. So I will start with a markdown. So this is our first notebook, corresponding of lecture 2. If you like, you can even date it, but it's always good. So, and it will be auto-saved. But as soon as you as soon as you have something in there, it's good to rename it. So I will rename a notebook. I will rename it here MCS 260 Lecture 2. Which is a good name, but sometimes if you have many notebooks, it's much better to give it a more meaningful name. So the better name is actually First Steps. It's our first step. A new section plus insert, and it will still be a markdown. So I will explain here how to use the format conversions. So you may have been thinking this when I was explaining the binary number system. Why do we actually have to know this? Well, perhaps as a computer scientist, and I've been told that if you're a true computer scientist, then you're lazy. So what actually you should remember is the way how a computer can do this. Here I have executed our first statement. So this is a code cell, that's the default cell. And I typed in bin. Bin is a function. And 1, 2, 3 is the input. So let me document this. So we executed the statement, the function, or we bin on the decimal number 1, 2, 3 and obtained the string representation of the binary number. The binary number that represents 1, 2, 3. So this is very useful, even if you have to do this by hand, and you won't be able, and you won't really need to do this by hand in this course, but if you need to be doing this, so this is the calculator step. Hex gives you the hexadecimal representation. Okay. Notice the difference, 0b and 0x. Notice also how do I know that it is a string? Well, notice the quotes, and these are the right quotes. Can I also go back? Oh, yes, I can. So in order to go back, so let me say what I'm going to do. So to convert a number from binary into hexadecimal, we use the eval function. Let me demonstrate this. So I will make so here is another important aspect of using a calculator. So you can take the result of a function and save it into a variable name. So I should emphasize this. What we did, we called the function bin and saved the output in the variable b123. In a separate code cell, we requested the value of the variable b123. So b123, as I did in the last lecture, I put it between right quotes. It's not b123. So you can see the markdown formatting. It's also written in a very special fashion. So it's actually not b123. It's the variable that refers to the object which represents the string representation of the binary number, the number 123. So in some sense there's only the number 123, but in decimal notation we are used to call it 123, but actually it is the number 123, and you can write it in infinitely many ways. Perhaps, yes, in many ways you can write it. All right, I should actually not stray too much. The eval refers to the interpreter. So with eval, I'm evaluating. So this is important. We talked about the interpreter. The eval evaluates the expression defined in the string stored in the variable b123. So in a way, I have already shown the delay in the printing. So you first assign and then you look at the value in two separate code cells. But you can store, I mean, your programs are actually stored also as data, and they are executed by the interpreter. In a way, putting quotes around something is just delaying the evaluation for later. All right, that's the first part. How can you very quickly convert a number from decimal into binary, and how can you go back from binary? So if you want to do this rather quickly, so I can type in 0x7b, and that should give me 123. So I'm evaluating an expression. So, and that will work. So miraculously, I still haven't done any errors. So this is still a very clean notebook. At this point in time, if you are a little bit carelessly or not paying attention, you may have gotten an error. Don't worry about this. So I will now, in the second part of this notebook, illustrate. So I will make a new title, how we develop our programs. So a second section, our first program. So traditionally, conventionally, the first program in any language prints hello world. With Python, this is a little bit trivial because it is only one statement. Print hello world. There it goes. So in the Jupyter notebook, so it's also sometimes a way to advertise Python. I do not think that there are many languages where you need fewer statements. What you can now do, we are sure that this program runs. We can now take this code and put it into a .py file. I will do that in a minute. To make this program a little bit more interesting, so every program has input and output. So this program, if you like, is kind of this program only had output. So there was only output. So we were printing, print is going output. So I had once a discussion with a student, is output going from the computer to you or from the user into the computer, from the user outwards into. As a computer scientist, you replace yourself, you often put your head inside the computer. So output is always going from the computer towards the user. So you should change your perspective a little bit. So you should think more objectively. So to define input, we use the input statement. So in some sense, Python went from Python 2 to Python 3, where they wanted to redo things correctly. But you can see that with print, they were actually not so much consistent because they have the input now an input statement. So how does the input statement work? Well, it's good to think about an example. So we want a personalized greeting. So the program will ask first, or who is there? So prompting the user to provide a name. There are many things that can go wrong already. So the advantage of a programming environment is that you can check this. So you can test this out. There is also the help, by the way, but I will not refer to this. So you could do help input. But here is how the statement goes. So you provide the prompt. Who is there? And it's a statement that returns something. Again, thinking about input and output, the input brings it into the computer. So let me run this. So here you now see the star. So the system will actually hang. It will wait for me to type. So who is there? Well, it is me. So I type ME and then I press enter. And you see that the star disappeared. And as a result, oops, I did make a mistake. So let me cut this. As a result, if I type name, I will see the string me. To complete this program, so our program will have two statements. I will do print name. Okay, I have my first program and I'm 50 minutes in, again going over time. I have my first program with two statements, and now actually I should show how to run this program. So I will make a new terminal window. here you see the terminal window, and I practice this. So I have my hello program, and I have my hello who's there. So that was my second program, and now I forgot how I named it. So it's hello there. Here you see me asking for the source code. So this is a Windows PowerShell that is executed within the JupyterLab environment. So within one JupyterLab environment, I have a shell, I have a PDF file, and I have a Jupyter notebook open. Now, how do I run this? Well, I do Python hello there.py. Who is there? It is me. So this is the command line execution that executes these two statements. So I should actually show how to, and I will do this. So I will indicate how you can use an editor. So we have I will do this very quickly, print hello world. So this is my first program. You see there are many things that can go wrong. So I was using single quotes, but now I'm using double quotes. Double quotes will work as well. What won't work is that you start with double quotes and end with single quotes. So already here there are things that can go wrong. So let me use single quotes, not to confuse. So it is untitled and it is a .text file. So I should here rename this and rename the extension. So this is my hello world. And now you see that you must have the extension .py because then it is recognized by the Python interpreter and it will be executed, or it is not executing. It is not here because I made a typo. And here you see the things that are happening. It has created the file. I have renamed the file, but the file is empty. So good that I made this mistake. So I have to save it explicitly. So there is an autosave, but it only takes. So I have to save the file. Save the Python file. So Control S is the shortcut. And now I can execute it. So now you see that there is the Python hello world. So with the arrow up keys, you save yourself a lot of typing. So now you see the hello world. You can see from my mistakes, fortunately, that I make them because I want to indicate that there are many things that can go wrong. From the output, you can see that there is documentation. So this is very pedantic. So I start every program with a line. What is the program actually doing? Then I have a longer documentation string. Triple quotes. So we have single quotes, double quotes, triple quotes. Triple quotes are used for indicating long strings that span many lines. Okay, I'm going over time, so I hope that this was not too confusing and that this was helpful. Again, what is important from this lecture is that you know Python is an interpreted language. We use the Jupyter Notebook to define our algorithms, to do our computations, to develop our programs. Running a program can happen directly from a PowerShell window as I have demonstrated here. So that is it. Look at the exercises. So the exercises, at this point in time, you should be capable of doing the exercises. Exercise 2 asks you for a first name and a last name. So typically when you type in a string, if there is a space, you may only see the first name. So that's why you have to prompt twice and give two questions, ask two questions. Okay, so this was our second lecture on computers, programs, and numbers.